Hello, thanks for joining this plenary session of the Amaldi meeting. It's been very exciting and we have a very exciting session. I'm Gabriela Gonzalez, Gabi, professor at Louisiana State University. And we will start from space with Sarah Paczkowski. I'm not sure I'm pronouncing your last name right, sorry about that. With gravitational wave instruments in space. Sarah, I will tell you at the 25-minute mark. Please go ahead.
Yes, thank you for the introduction. Good morning, good afternoon, or good evening, and welcome to my talk about gravitational wave instruments in space. So I'm giving this talk on behalf of my colleague, Shweta Shah, who unfortunately couldn't make it today. So you've seen a lot about the success of gravitational wave observations with the instruments we have on Earth. And so you may wonder why we're speaking about gravitational wave instruments now from space as well. And so the reason we want to observe gravitational waves also from space is that there are a number of exciting sources which emit gravitational waves at millihertz frequencies and around. And here I've just captured three examples. So one of these are compact binaries in the Milky Way. Another type of sources that we are looking forward to observe are massive black hole binaries. And as a third example, I selected the extreme mass ratio in spirals, or short MRIs. And what is more, with gravitational wave observatories from space, you can also predict the coalescence times and locations for ground-based detectors for some sources. And I like to imagine that in simple terms as the ability to set your alarm clock right, so that you know when to be present and measure. Well, but these exciting sources, they don't tell you why we actually have to go to space. So the thing is that ground-based instruments are limited to frequencies of maybe about a few hertz, also with future observatories, and that's mainly due to seismic and gravity gradient noise. And in addition, it's difficult to increase the arm length even further to improve the strain sensitivity. So that's why we have to go to space. Now, LISA is the ESA, or European Space Agency, mission to do exactly that, to observe gravitational waves from space. And on ground and in space, the basic principle of the measurement is a Michelson interferometer, but in this LISA constellation, that might not be immediately visible. Indeed, LISA is characterized by 3 satellites which form an equilateral triangle where each of these arms has a length of 2.5 million kilometers. And this triangular constellation is trailing behind the Earth on its orbit around the Sun. And during this orbit, this triangle is rotating in what's called a cartwheel motion, such that the distances are kept as stable as possible. Now, if we look a little into this constellation, you can see that each of these 3 satellites that we have, they contain 2 lasers with associated interferometry, as well as 2 test masses, and laser light is interchanged in between the satellites. And now the test masses or proof masses, they mark our gravitational reference points. So that's why it is important to protect them from all non-gravitational forces, so from all other influences except for the change in distance, which reveals the gravitational waves. So this gives you some view of the technology that we need to observe gravitational waves in space. But let's look at this a little more systematically. So this is quite a short talk, so I'll focus on 2 main aspects here. And these are interferometry and the isolation of the test masses from disturbances. So on Earth, the gravitational wave observatories are characterized by a number of features, but one of or two of these are that homodyne interferometry is used and that high laser power is used as well. In space, that's going to be different because heterodyne interferometry is needed and little power will be received at the far satellite. So if you want to summarize the experimental path in one sentence, you could say here that we want to measure with picometer accuracy over millions of kilometers at millihertz and sub-millihertz frequencies. And correspondingly, when it comes to the isolation from disturbances on Earth, the detectors use heavy mirrors which are mounted on an elaborated suspension system. And in space, you don't have mirrors, but you have test masses. And you need to ensure that they are free-falling to the required level that's needed. And this means that, again, to limit all undesired residual acceleration. So ideally, you would go for 0, but what is needed is a level of femtometers per second squared at sub-millihertz and millihertz frequency. So that's sort of the framework that's being operated in. And what you can see is that moving to space clearly removes the seismic noise barrier and allows for longer arms, but it also brings along the above experimental challenges. So these have been known for quite some time, and in the last years, some progress, and actually a lot of progress, has been made. So at first, let's look at the results from the LISA Pathfinder mission, what concerns these experimental challenges. So LISA Pathfinder, or in short LPF, was a mission that was developed for quite an amount of time and extensively tested before launch, as you can see, for example, in this picture down here. And finally, on December 3rd, 2015, it was launched on a Vega rocket, as you can see here on the right, and operated until the final shutdown on July 18th, 2017. And so to illustrate a bit the concept of the LISA Pathfinder mission, the idea is to take one of these 3 LISA arms and to shrink the arm length from millions of kilometers to just about 38 centimeters, such that the whole LISA arm fits into a single satellite. And with this, the aim is to prove that an ideal free fall on a satellite can be achieved to a sufficient level. And to do so, and in addition, key technologies for LISA have been tested. So we like to think of LISA Pathfinder as our laboratory in space, because actually one could do many measurements and also very many detailed experience on the different subsystems. And this was a very unique chance to do a bunch of experiments, and also very limited in time. So that's why a tight schedule had to be developed, and all of this was planned, then tested on a mission simulator before the commands have been uploaded via telecommands to the LISA Pathfinder satellite, which executed the experiments on measurements, and then the data was downloaded and analyzed as quickly as possible. And when you operated LISA Pathfinder, you had always to remember that only a selected number of data channels could be retrieved at any one time, and that the sampling rate was limited due to the transfer from space back to Earth. So if we look now at the satellite and at the instrument in more detail, you can see that it consists of 2 vacuum tanks with the 2 free-falling test masses in between, and an optical bench in the center. So this optical bench is a fixed zero-draw plate, and a number of beam splitters and mirrors were mounted on there, as well as the photodiodes that you can see. So this was testing a lot of interferometry in space. So one of these two key aspects that will guide us through the talk, and the test masses and the gravitational reference system around them allowed us to measure the very small residual acceleration. And so indeed, here's the result from LISA Pathfinder, where on the y-axis you see the amplitude spectral density of the residual differential acceleration and the frequency on the x-axis. And what you can see is that immediately in April 2016, the LISA Pathfinder requirements were met with ample margin. So in this plot, lower is always better. And so in February 2017, we actually obtained the measurement that's shown here in red, and which is not only even better than the one before, but it's also below the LISA requirements already, and with a level of around 2 femtometers here, we are so we have managed to measure the quietest place that could ever be measured. Even though it was so good, let's have a look what was limiting at which frequencies. So in around the millihertz frequencies here, the Brownian noise from residual gas was limiting. And so around these test masses in the electrode housing, there are some particles still remaining which experience this Brownian motion and make this residual acceleration. So at lower frequencies, actuation noise and radiation pressure from the laser are contributions as well as other things, but a certain percentage of this noise is not been known yet, and details on this differential acceleration can also be found in the talk by Eleonora Castelli, which you may listen to on the recording. And at higher frequencies, the noise of the optical sensing system, or short OMS, was limiting. So some more details on these two key parts. So as I said before, the gravitational reference sensor that you can see here contains the test mass, which is surrounded by electrodes, and the performance of this system is influenced by a number of things, but one of them is Brownian noise from residual gas around the test masses, and so that's minimized by the wide vacuum system that's being used, and by the fact that during LISA Pathfinder there's been constant venting to space, and so the vacuum became better with time. And in addition, there's the combination of charge and stray potential, which may lead to noise. And so this way, the test mass was discharged regularly via UV light. So this avoids a wire that connects the test mass rigidly. And the gap size was chosen larger than it was chosen for other missions, from 3 to 4 millimeter, depending on the direction. And one influence in this gravitational reference sensor is the electrostatic actuation. And these electrodes, they can also do sensing. So the gravitational balancing on the satellite determines the amount of electrostatic actuation which is needed. And so in the design process of LISA Pathfinder, a static gravitational field with an acceleration of 650 picometer per second squared was expected, but then in flight, due to excellent balancing and like taking the precise weight of each of the components that finally gets on the satellite, this acceleration could be limited to less than 50 picometer per second squared. And this allowed to reduce the actuation authority, and so to reduce the voltages that can be applied at maximum in the system, and in turn to reduce again the voltage noise, and this reduces the force noise from the actuation onto the test masses. Now let's look at the other key system that we want to study here. So that's the optical metrology system, or in short OMS, and it measures the distance with respect to the required reference mass with a required accuracy of 9 picometers per square root hertz using heterodyne interferometry. And here's a picture of the optical metrology system. So in the center, you can see the optical bench with the mirrors and beam splitters. And here is the vacuum tank. And you can see that there's an optical window so that the beam can hit the test mass, which is inside the vacuum tank. And this LISA Pathfinder optical metrology system consisted of an optical bench, which hosts 4 interferometers, and one of them is the X12 interferometer. So it measures the position of test mass 2 with respect to test mass 1. And you can see here that the measurement beam in red does hit both test masses, while the reference beam stays on the optical bench. Then we also have the X1 interferometer, which measures the position of test mass 1 with respect to the satellite. And then we have 2 auxiliary interferometers, which help to get the precision that we needed. And one of these is the reference interferometer, which measures the common mode path length fluctuations. And here you see that the 2 beams do not hit the test masses at all. And the 4th interferometer on this bench is the frequency interferometer. And it has intentionally an unequal path length, and so it measures the laser frequency fluctuations. And this measurement was used to stabilize the laser frequency on LISA Pathfinder. And this combination allowed us to achieve the measurement that is shown here. So on the x-axis, again, we have the frequencies, and on the y-axis, we have the displacement noise in meters per square root hertz. And what you can see is that at lower frequencies, these measurement of the displacement is dominated by test mass motion due to Brownian noise. Then we have some pickup of the spacecraft motion via what's called the TTL coupling. And if you want to know more about that, then have a look at the recorded talk by my colleague Marie-Sophie Hartig, which took place on day 3. And here at higher frequencies, we can really see our sensor noise. So we can see that we measure with an accuracy of around 30 femtometers per square root hertz here, and that our dominating noise contributions are phase meter readout noise and remaining frequency noise. Plus we have a smaller contribution from shot noise and relative intensity noise. So yes, these were just a lot of details on 2 subsystems, but in total, LISA Pathfinder was a very fruitful experiment. And here it shows some random examples with a number of further references. And so these are all interesting results, and we could learn quite a lot from LISA Pathfinder. So all the way to temperature measurements or even measurements of the gravitational constant. And I cannot explain all of them here, but encourage you to have a look in what's most interesting to you. But there has been even more tests than LISA Pathfinder of what concerns technology for gravitational wave observation from space. So let's have a look at other missions. So let me mention the TaiG mission, which also consists of a triangle formed by 3 satellites with a planned distance of 3 million kilometers in between them. And this is a project which is centered in the Chinese Academy of Science, or short CAS. And the Taiji Pathfinder was launched at the end of 2019, and you can see a photo of the satellite here on the right. And this satellite demonstrated local laser interferometry, a free-floating test mass, as well as drag-free control. And the next step in this project is Taiji Pathfinder with 2 satellites and inter-spacecraft interferometer. Then the other project I would like to mention is Tianjin, and this is a planned future gravitational wave observatory from space, where again we have a triangle of 3 satellites, but this time it's centered around the Earth. That's sort of an obvious thing to know. And this project is centered in the Sun Yat-sen University in the south of China, in Guangzhou region. And also in this project, the Tianjin-1 demonstrator mission was launched at the end of 2019. And here's a photo of the main contributions, or like instrument parts, that have been on that satellite. And also here, local laser interferometer, free-floating test mass, and drag-free control could be demonstrated. And in this project, the next step is again to fly Tianjin-2 with 2 satellites and an interferometer in between them. If we extend our look further, then we can also see that GRACE follow-on and its inter-satellite interferometry is interesting for future gravitational wave observatories. So GRACE follow-on is an Earth observation mission where a pair of 2 satellites with a distance of approximately 200 kilometers in between them is flying over the Earth. And as sort of an add-on at a rather later stage of the development, a laser ranging interferometer, so that exchange light in between the 2 satellites, was added. And this is what you can see here in the schematic. And the characteristic can be seen as this sort of half rectangular shape here, where the interferometry is constructed around the microwave measurement and as well as gas tanks, if I remember correctly. So this has been launched in 2018, and here's an example time series measurement of the GRACE follow-on laser ranging interferometer while this pair of satellites flies over the Himalayan mountain region. And you can see here that a change in the inter-spacecraft distance on the level of a few 10 micrometer was measured, and that you have here this larger signal while you're flying over the higher mountains where there's the more mass accumulated. So GRACE follow-on and its inter-satellite interferometry are a very good test of a laser link acquisition that worked in space, and this worked very quickly. And also, this laser ranging instrument could provide uninterrupted measurements for more than 1,500 orbits so far. And also, it worked again much better than was originally required, as you can hopefully see in this diagram here on the bottom, where the requirement was at 80 nanometer per square root hertz, but the actual measurement here is way below that. So you've seen now a lot of technology tests that have already flown, and you may wonder what remains actually to be done. And I want to illustrate this a little bit with some highlights of the laser development. So let me give a very short laser timeline. So In November 2013, the Gravitational Universe Science theme was selected by the European Space Agency mission as the theme for the L3 mission. And after they called for mission concepts, the LISA proposal was submitted in January 2017 and then selected in June of that same year. And since then, the development is in progress, and this year we are concluding what's called the phase A, where you show the feasibility, and at the end of the next phase, sort of the gate towards final mission adoption, is a preliminary definition. And so some work for scientists remains, despite all the good results that we've seen already. And again, here I can only give examples, but one thing, for example, relates to the 2 optical benches that we have on each satellite.
You have 5 minutes left.
Great, thanks. Yes, then we have on each satellite, and these optical benches, together with a telescope and the respective test mass, they contain they combine what's called a moving optical subassembly. So these 2 things on one satellite, they need to be connected, and a laser light needs to be exchanged from one side to the other, and the phase fidelity of that connection is studied in more detail, and also implications of these very little motions for the local gravity field on the satellite are being studied. And among these and many more things, one task is to also keep track of the development, and this is done via performance modeling, so to combine models of all the subsystems that are involved into a model of the total performance. And to answer questions like if we would change this and that, or if this and that component were more noisy, how would it affect the science that we can do? A set of certain figures of merit is being defined and constantly refined. And the same refinement is being applied to some of the noise mitigation concepts. So maybe you have heard that laser frequency noise plays an important role in LISA, and this noise is mitigated in 2 ways. So at first, the lasers are stabilized, and the current plan is that this is being done by a cavity. And in the next step in post-processing, an algorithm called time delay interferometry, or short TDI, is being applied. And this is part of what's now called the initial noise reduction pipeline, which has been explained in more detail in a talk by my colleague Martin Stab. And another example that I want to briefly mention here is tilt-to-length noise. And this again is mitigated in many ways, and at first in hardware, where one example is that the alignment can be then finally even adjusted still in flight. And again, this noise, or what remains of it, shall be subtracted in post-processing. And in addition, the optics construction facilities are being developed right now. And the goal is to further streamline the construction process. And that's really important because a space mission requires extensive testing. So that means that a certain number of qualification models will have to be constructed, in addition to the construction of 6 benches that will actually fly. And here in this picture on the right, you can see a photo of a clean room facility at the UK Astronomy and Technology Centre in Edinburgh, where you can see that the coordinate measurement system and such a robot arm to streamline the construction process and to transfer the technology that has been demonstrated already there, that this is already present and the process is going on. And in addition, test facilities are being developed. And one example is the test stand for the LISA laser phase fidelity measurement that you can see a photo of here on the right. And you can already distinguish one of the key features, that it's actually movable. So you can take this test stand and move to wherever is the laser that you want to test. And in addition, a picometer high signal optical bench for phase meter testing has been constructed, and that's shown in this photo down here. So with that, I'd like to summarize briefly what I've said today. So concerning gravitational wave instruments in space, I hope I could show good evidence that a lot of progress has been made in the past years, and that 3 dedicated demonstrator missions have already flown, and especially from LISA Pathfinder, we could find unprecedented performance. And in addition, valuable experience on intersatellite interferometry has been gained from GRACE follow-on. And LISA is on its way to mission adoption in 2024. And with this, I would like to thank you for your attention and thank very many people. A number of them are shown here, but not even all. And well, thanks.
Thank you, Sarah. That was exciting news. Do we have any questions? Please raise your hand in Zoom if you have any. In the meantime, I have a question. I know that you may not be the person to know the answer, but do you know the similarities and differences between the Tianjin mission and the LISA mission? Sarah, you're muted.
Hi, yes,
and it's okay to say you don't know, of course, since I know
yeah,
you're working.
I'm not sure, since I'm not working on this particular mission. You said, sorry, you said Taiji mission?
Well, the Chinese mission orbiting around the sun, the heliocentric mission.
Yes, therefore the heliocentric mission, I can only say one difference, right? And that's the arm length of this triangle. So I think that is planned to be 3 million kilometers for the Chinese mission and 2.5 million kilometers for LISA. And so top of my head, I mean, that changes a number of things, right? What concerns laser power, telescope, and many other things. And then may also change the sensitivity. And but sorry, I can't compare them right now.
That's of course. Any other questions from the audience? We have 100 people participating. Salvo, please go ahead.
Yes, thank you. Thanks, Gabi, and thanks to the speaker. So sorry if you have mentioned this and I have missed it. I had some issues with my internet at times. As the reason for the glitches that were observed in LISA Pathfinder being fully understood, and is it expected that they might be an issue for the actual mission? Thanks.
So I believe the glitches could be classified into 2 categories. And to my current knowledge, there is a lot of improvement in understanding one of these 2 categories at least. Let's sorry, give me a second. So the detailed work has been done by Lorenzo Sala, I believe, from University of Trento, together with Eleonora Castelli. And I believe that simulations have been underway to see if that comes from a certain component on LISA Pathfinder. And right then, the answer depends if this component will be in a similar, will be similarly in LISA as well. But I would like you to refer. I would like you, yes, to refer you to the experts there. And I believe for certain, right, if you build such an instrument, even if things work well, then you'll have glitches still. And that's also their impact is being studied, and assumptions are being made from what we saw on Pathfinder and how this could translate for LISA.
Thank you.
Thank you, Ira, for the comment. Let me read it. I was the one confused. Tianjin uses a geocentric orbit with much shorter arms, 100,000 kilometers, and is optimized for higher gravitational wave frequencies than LISA. Taiji is more similar to LISA with minor differences, like Sarah mentioned, like the arm length, and others will know more than us. But thank you, Ira, for the details. Okay, let me take the opportunity then, the prerogative as a chair, and ask you another question. You mentioned that there are several things that need to be done. Many of those seem to be designed, but some are experiments, right? What experiments are going on and in which labs? It's a large collaboration, as I know.
Yes, so I may not know of all the experiments that are going everywhere, of course. So so there's telescope testing, which I believe is going on in Florida. Then we have this experiment about the phase fidelity in between the two moving optical sub-assemblies of one satellite that's being done in Hanover. And then there's a lot of development also in Spain, and as I mentioned, in the UK, and there especially towards the actual construction and how to optimize and automate this process as much as possible. Then, as to my knowledge, there's also work ongoing, right, in the labs in Zurich and Switzerland. In LISA Pathfinder, we found a very minor thing, right? You saw everything worked really well, but there was a very minor thing concerning the actuation electronics, and that work, I believe, is being taken forward in the Zurich team, and of course at the University of Trento, who are the sort of our experts for the gravitational reference sensor system. So I hope I could mention a lot of that, and do credits to the many people involved. And oh yes, so I'm sorry, I almost forgot about labs in Paris, who also have a LISA on a table experiment. And sorry, but I forgot about
that's okay. Yeah. Sometimes I think that people think that these space missions happen by magic, by people only working in the ESA labs, but it happens everywhere. It's a big
yes, but inside ESA, there's development done as well. And we have this huge ESA consortium where also a lot of work is being done.
Right. Okay, let me thank Sarah again for a very nice talk. And we'll move to modeling, a talk by Francois Foucart, assistant professor in the University of New Hampshire, talking to us about modeling gravitational wave and electromagnetic signals from neutron star mergers. So this is space and ground.
Okay, thank you. And thank you for inviting me to speak with you today. So yeah, in this presentation, I'd like to give you an idea of some of the work that is being done to model the gravitational wave and electromagnetic signals powered by neutron star mergers, by which in this talk I will mean both the mixed black hole neutron star binaries and binary neutron star themselves. So 2 out of the 3 systems that have been detected so far. And there will be a talk later in this conference, in the last session by Harald Pfeiffer on the 3rd type of binary black hole systems. So in this talk, I'm going to start by looking at some of the things that we can do with neutron star mergers, the physical questions that we can answer, specifically focusing on what we can do with neutron star mergers that is not possible for binary black holes. And then we'll look in more detail at modeling of the gravitational wave signal and specifically finite size effects in the gravitational waves. And finally, at matter outflows from these mergers and how to connect them with kilonovis signal, the optical infrared emission associated with radioactive decays of elements produced during the R process in the matter ejected by mergers. And over the course of the presentation, I'll try to emphasize the role of numerical simulations and also where the limitations of numerical simulations may impact still our ability to reliably extract information from observations of these systems. Before getting into any of that, let me give you an idea of what one of these systems might look like according to a numerical simulation. This is a black hole neutron star binary, where the black hole is initially on the right, the neutron star on the left. With the simulation started here a few orbits before the merger. In a system like this, the neutron star is initially tidally distorted by the gravitational field of the black hole, and then in this case disrupted by the black hole, leading to the ejection of a few percent of the solar mass of very neutron-rich matter here in the tidal tail, and the formation of a hot, massive accretion torus around the black hole, in this case, maybe 10% of the solar mass. That torus is then going to continue to evolve over multiple seconds and continuously ejects matter into the surrounding interstellar medium. So those are the kinds of features that we are going to try to study when we do numerical simulations of these mergers. It's finite size effects during the latent spiral and the merger, ejection of matter, and formation of accretion disk and the subsequent evolution of that accretion disk. Those are what is going to be important for finite size effects in the gravitational waves and for electromagnetic emission. Well, the first thing that we have at our disposal when studying neutron star merger that was not available for binary black holes, of course, is the potential for a bright electromagnetic counterpart to the merger. And that allows us to do some physics that is much harder to do or impossible to do with binary black holes. For example, in this conference, we've already heard a fair amount about the fact that if you get an electromagnetic observation and you use it to find a host galaxy and get a redshift to the system with that electromagnetic observation, you can use that redshift and the luminosity distance from the gravitational wave observation to measure cosmological parameters, including, for example, the Hubble constant. You can do that even better if you have an idea of the orientation of the system thanks to electromagnetic observations. Another thing that can be done, and that was already done for GW 170817, the first neutron star merger observed, is using the joint detection of a gravitational wave and electromagnetic signal, and some constraint on the time delay between the emission of these signals to constrain the relative speed of propagation of gravitational waves and electromagnetic waves. And that has led to the best measurements so far of the speed of gravitational waves. There are also a number of interesting questions that are more related to nuclear physics that we can try to solve with neutron star merger. The first has to do with the composition of very dense matter. Matter at the center of a neutron star has densities comparable to the density in an atomic nucleus, At the very high density and low temperature that exist in that core, we don't know what the strength of nuclear interactions between all of the densely packed together particles are. We don't even really know what the composition of that core is. It could be still mostly neutrons with a few protons and electrons as farther out in the neutron stars. Or it could start creating strange quark matter or a phase transition to something completely different, for example, a quark-gluon plasma. But for any nuclear physics model that you might have for what happens at those densities, you can build an equation of state for the matter in equilibrium, and from there build the macroscopic properties of neutron stars. For example, the mass-radius relationship shown here for different parameterized equation of state. So we can go from those microscopic nuclear physics properties of the dense matter to observable macroscopic properties of neutron stars. And so if we can make a measurement of the mass and radius of a neutron star, or the maximum mass of neutron star, or using gravitational waves, the mass and tidal deformability of neutron star instead of the radius, which is very strongly related to the radius, we can actually put constraints on the nuclear physics inside neutron stars. A second important question that we are going to try to answer with this system is the origin of heavy elements. And in particular, we are going to be interested in all of the light yellow elements on this plot, which are formed in neutron-rich environment through what is known as the rapid neutron capture, or R process nucleosynthesis. And we know from GW 170817 that very likely at least some of the R process elements are produced in neutron star mergers, but the question that we would like to answer is how much do neutron star merger contribute to the global production of these elements in the universe? And for that, we need to know how much matter is ejected by any given neutron star merger. We will see that we also need to know the composition of that matter. And of course, we need to know the event rate of these mergers, which hopefully will become better and better known as more gravitational wave observations become available. And then we can compare that with actual observations of the abundances of our process elements, both locally, but also, for example, in low metallicity stars, which allow us to study the time evolution of that R process enrichment, getting an idea of what was enriching the universe in these R process elements at earlier times. So those are some of the physics and astronomy questions that we are going to try to answer with these systems. Now, the observation that we are going to have at our disposal are summarized on this plot, which I borrowed from Rodrigo Fernandez and Brian Metzger. In a neutron star merger, either neutron star or black hole neutron star merger, you are going to have a long phase of gravitational wave driven in spiral, of which, as you probably know, we only observe the last fraction of a second to seconds to hopefully in the near future minutes. That late in spiral and merger is where we get the gravitational wave signal from. In terms of finite size effects, the finite size of the neutron star, as we see, is really only going to matter during the last few orbits. Before that, the neutron star largely behaved like a point mass in terms of gravitational wave emission. Then there's a very short merger phase that lasts maybe a few milliseconds, during which the matter is entirely reorganized, and some matter is starting to get ejected, for example, in the tidal tails that we've already seen in the previous movies, but also possibly during the collision of two neutron star and formation of either a black hole or a more massive neutron star remnant. The result of that merger is typically either a black hole or a neutron star surrounded by an accretion disk. And that accretion disk is going to continue to evolve over multiple time scales, up to multiple seconds after the merger. And during that time, it's going to eject matter relatively isotopically in disk vanes, and also in more, at least in some systems, in more narrowly focused relativistic jets. So from an observational point of view, if you are looking at a system from the barrel of the jet, let's say here or here, you will see a gamma ray burst. And if you are farther off axis, you may see the afterglow from that gamma ray burst, but you will also see the electromagnetic emission associated with the more isotropic matter outflows coming from the disk, and coming from the merger itself. That emission is largely powered by the fact that in that neutron-rich ejecta, you are going to get rapid neutron capture nucleosynthesis, which is going to first form some heavy unstable elements that then radioactively decay towards stable elements. And initially, that the energy released by this radioactive decay is released in part in neutrinos that just escaped the system, and in part in particles that are thermalized in the ejecta. But at some point, the ejecta is going to become optically thin to optical and infrared photons. And at that point, the energy is going to be re-radiated in the quasi-thermal emission that is going to rapidly evolve from optical to infrared. And that's what we call a kilonova. And we'll see that the kilonova depends on the mass ejected, the properties of the outflows, and the type of R-process nucleosynthesis that was happening. And so using kilonovae, we can get an idea of what was going on during the R process, what elements were produced, and also what the properties of the merging compact objects were. So those are the things that we are going to try to model. Okay. So now for the second part of this talk, I'm going to focus more on the gravitational wave emission and our current models for that emission. Now, when we talk about neutron star merger simulations or model of specific neutron star mergers, we are mostly going to be worried about finite size effects on the waveforms, largely because the other effects of masses, spins, and so on, are better studied using binary black hole simulations that tend to be more accurate and also present largely the same effects. So in terms of finite size effects, we can see the impact of the finite size of the neutron star on these plots here, which show waveforms, numerical simulation results for the waveform of binary black hole in blue, black hole neutron star in red, and neutron star in white. For systems that have equal mass and non-spinning components. And when there is a neutron star, all neutron stars are set to a relatively large radius, in this case of about 14 kilometers. And you can see that, as I mentioned before, at early times, all of those waveforms look basically the same. And then at late time, there starts to be significant difference. So if we zoom in on the late time behavior at the bottom of the plot here, you can see that the first effect is that the neutron star binary starts to evolve faster. The frequency and amplitude increases faster for neutron star binaries than for black hole binaries. And the dephasing is going to be proportional to the tidal deformability of the neutron star, which scales like the radius of the neutron star to the 5th power. So that's one way in which we can hope to constrain the size of neutron stars is by measuring that dephasing in the waveform. The more obvious effect of the finite size of the neutron star, of course, is the merger signal itself. But you can see that for binary black holes, the frequency increases up to the point where you form a single horizon for the merged black hole. And then you have an exponential decay of the ring down of the black hole that is shown here on the right. For black hole neutron star system, first, the signal does not go to as high of an amplitude and frequency. There is a shutdown here, which in this case is due to the disruption of the neutron star by its black hole companion. Once the neutron star is disrupted, on the other hand, there is basically no gravitational wave emission anymore. So you get a smooth shut off here for the black hole neutron star system. And for neutron star binaries, you also stop the growth of the amplitude of the signal, but then at later time, you get those high frequency oscillations, which are due to oscillations of the neutron star remnant formed in this system. They wouldn't be present if the remnant collapsed to a black hole instead of forming a neutron star, as is the case in this simulation. There's a lot more information about the finite size of the neutron star in that merger and post-merger signal. In particular, for example, the frequency of the gravitational waves after the merger is very strongly correlated to the equation of state of neutron stars. When or whether there is a shutdown of the emission of gravitational wave in a black hole neutron star merger is very strongly dependent on the size of the neutron star. So we would like to eventually get to study this merger and post-merger signal, but that is very hard with current gravitational wave detectors because these signals tend to be in the kilohertz to multiple kilohertz regime. And so at the moment, we actually end up being more sensitive to the smaller dephasing effects at early time than to the late merger signal. But one important objective of next generation ground-based detectors will be to get better sensitivity at high frequency so that we can actually start to do more of these studies of the high frequency post-merger signal and get information about nuclear physics from there. All right. Now, if we want to actually use neutron star merger observations to study the equation of state of neutron star, we need to have models that include finite size effects to sufficient accuracy. And that requires the construction of analytical models that include finite size effects and testing and or calibrating on numerical simulations, which within numerical accuracy are going to allow us to see what the correct answer is according to this general relativity. And so there's usually a joint development of models by improving both numerical simulations and analytical models at the same time, and then comparing them to each other. In terms of numerical simulations, there have been a fair amount of progress over the last decade or so. Maybe the most important one being the construction of codes that can converge faster than second order. There have been different methods developed to do that, including the ones in this paper here. But overall, there are now quite a few groups that are capable to get similar accuracy for these waveforms, to get to phase errors at the time of merger, which are of the order of a fraction of a radian, for simulations that are 10 to 15 orbits long. Now, the longer the simulation is, the more we are going to accumulate errors. So this is typically the length that we can do right now and still resolve finite size effects. So a fraction of a radian should be compared to the actual impact of the finite size of the neutron star on the phase of the waveform, which over these lengths of simulations is a few radians. Two examples are shown here. On the left is results from the SACRA code for a neutron star binary that evolved for about 15 orbits. This shows the phase error in the waveform as you increase resolution. You can see that for the higher resolutions here, you get indeed to a few tenths of a radian at the vertical line here, which shows the peak of the waveform. If instead we look at the simulation on the right, which is a black hole neutron star binary generated with a spec code. This one is a little bit shorter, 13 orbits, and at the time of merger here, which again is the vertical line, we end up with, again, errors of the order of a few tenths of a radian. So that's typically where we are right now. And before, before the merger, if you get a few orbits before merger, you easily get to a few percent of a radian instead. In parallel, there has been a lot of progress on analytical models of these neutron star merger waveforms. And there have been different approach to improving the models. Some models are directly calibrated to numerical simulations. Some free parameters in the model are fitted to the result of numerical simulations. Some models instead add new, more and more physics to the model, but in part also by looking at where the models, the existing models differ from numerical simulations and adding the physics that seems to be the most relevant to those differences. For neutron star merger, both approaches have been used, including in the papers shown here. For black hole neutron star mergers, all of the best models available so far do have some aspect of fitting to numerical simulations because there is no good analytical model for the disruption of a neutron star by its black hole companion. And so the shutoff of the gravitational wave signal at the time of merger is currently always done through a fit to numerical simulations. One thing to note in these models is that, for example, the black hole neutron star models only model at this point the 2-2 mode of the gravitational wave, the dominant mode. And we know that if we get to higher mass ratio, the higher order modes are going to be more important actually than the finite size of the neutron star, because as the mass ratio of the system increases, finite size effects in black hole neutron star merger become negligible. And so interestingly, as a result of that, what has been considered as the default analysis of the two observed black hole neutron star system currently published by the LIGO-Virgo-Kagra collaboration was done with binary black hole waveforms. Also, the analysis was also done with these two black hole neutron star waveforms and provided consistent results, also with slightly larger error bars. But for lower mass system, on the other hand, tidal effects would be significant and have to be taken into account. So now we have models of the gravitational waves, and we have numerical simulations. And knowing the error in the numerical simulations, we can see where the models start to get out of these error bars. That is what is shown on this plot here for spec simulations of black hole neutron star system. The top plot is pretty standard result for black hole neutron star merger with relatively low spin objects and relatively near equal mass systems. In this plot, which really only zoom at the very end of the evolution, you can see that the gray curve is the numerical simulation. And all of the others are different analytical models. I'm not going to get into the details of exactly what they are, but you can see that we really need to zoom to the last 2 cycles of the evolution to see a noticeable difference between the numerical simulation and the models. On the right, you can see the same shown as the phase error in the phase error as defined by the difference between the models and the numerical simulation compared to the estimated numerical error. And again, it's only at the very end of the evolution that the model differ from the numerical simulation. That's pretty typical, but there are some edge cases where there are actually noticeable biases in the models. The one I'm showing you here at the bottom is what used to happen if you had a spin on the neutron star, where you can see that the numerical simulation has a clear difference with all of the analytical models because some effect of the spin of the neutron star on dynamical tides close to merger were not included in the models. And I include this because it's actually an example of how we sometimes go about improving these models. That the reason I ran this simulation is because Tanya Hinderer told me that running with a spinning neutron star would likely break the existing models because some physics was not properly included in the existing models. So we run this and we indeed find that there is a difference. In the 2 years since we published this paper, Jan Steinhoff and Tanya Hinderer have developed a model that includes the spin of the neutron star, the effect of the spin of the neutron star on tides close to merger, and significantly reduce the modeling error for this specific type of system. So that's typically how things can evolve, is with that back and forth between numerical simulations and analytical modeling. All right. To conclude, let's see how modeling errors currently impact analysis of gravitational waves. So we can look at the one system where we actually did have some finite size measurements for gravitational wave signal. That's GW170817. You can see here the mass radius relationship and the region allowed by the gravitational wave observations for the more massive and less massive neutron star, which is slightly more constraining than what we previously knew from nuclear physics. But this is just one event, so hopefully we can do much better on that over the course of the lifetime of LIGO and Virgo and Cagra, and also by combining these gravitational wave events with, for example, NICE observations, which has already started to be done. Now here's the analysis done with different models, which is how LIGO currently estimated these modeling errors. Now this is in terms of the tidal deformability, but effectively this scales like the radius to the 5th power. And you can see the different curves here show you the results with different models. And the orange, blue, and green curves are all some of these modern models that have been improved over the last few years. While the purple magenta curve here shows you the result with an older model that is known to be less accurate. And so you see, even with the less accurate model, the difference is at the order of 10% in the upper bound here on that tidal deformability, if you look at the 90% intervals, which are shown by those vertical lines. And then if you take the modern models, they agree with each other pretty well within much higher accuracy. So at this point, modeling errors is not likely to be a huge effect on the inferences done on, for example, 170817. One open question, I think, is what is going to happen as we increase the SNR of this system, and especially if we get more sensitivity at high frequency, because it's at high frequency that the model differ the most from each other and differ the most from numerical simulations. So I think having similar studies for systems where we have high frequency sensitivity will be important to know the impact of modeling uncertainties on these finite size measurements in the future. All right, so that's what I wanted to say for gravitational wave modeling. Now let's briefly look at merger dynamics and how that leads to modeling of matter outflows and kilonovae. The general idea here is that if I have a neutron star, or black hole neutron star merger, it's going to eject some neutron-rich matter. The neutron-rich material is going to undergo R-process nucleosynthesis, leading to the formation of heavy elements. So what I'm showing you here is the relative abundances of the elements produced as a result of the R process in red as a function of mass number. This is for very neutron-rich ejecta, typical of what you find in the tidal tail of a black hole neutron star merger. And you can compare that with the R process abundances inferred for the solar system in black, and you can see that it matches pretty well the high mass elements, but underproduce the low mass elements. The way to produce these lower mass elements turns out to be to have mass ejection of slightly less neutron-rich material. And so that tells us that if we want to understand our process nucleosynthesis from these mergers, we need to understand not only the mass of these outflows, but also their composition, which is going to be impacted by matter interactions. So to understand whether we produce these heavy elements here or the lower mass elements here, we are going to need to understand how much neutrino interact with the ejected matter and to include neutrino matter interactions in our simulations. Another important impact of the composition of the outflows is that these elements here, the lanthanides, and these elements here, the actinides, have much higher opacity than anything else on this plot. And so simply their presence is going to impact the kilonova signal. Because the kilonova comes from a radioactive decay of unstable elements that decay towards these elements here. And then when the ejecta becomes optically thin to optical and infrared photons, the energy is radiated as a kilonova. So if these elements are present here and here, so if we have very neutron-rich outflows, we are going to get higher opacity ejecta, and that has a significant impact on the kilonova properties. This is shown here on these studies by Dan Kaysen and collaborators. As you increase the amount of these lanthanides, these heavier elements, you see that you go from a short-lived bright kilonova to a longer-lived dimmer kilonova. And in terms of the spectrum of the kilonova, you switch from an optical kilonova to an infrared kilonova. So this is great because this means that we can use kilonova to get an idea of what kind of elements were produced as a result of our process nucleosynthesis and what the composition of the outflows are, which can be hopefully in the future connected back towards the properties of the merging compact objects. So now, what do we know from numerical simulations about these outflows, and what can we reliably model? Well, in terms of black hole neutron star merger, we know that there are two potential types of merger. One is very similar to the movie I showed you before, where the neutron star is disrupted by its black hole companion, leading to the ejection of matter in a tidal tail, the formation of an accretion disk. In this case, you can have significant contribution to our process nucleosynthesis and bright kilonova. The alternative is typically for higher mass black hole. The neutron star is still tidally distorted by the black hole, but it's going to reach the innermost stable circular orbit of the black hole before merging, and then it's just falls into the black hole, leaving nothing behind. In that case, there is no matter ejection, and also it turns out that the gravitational wave signal becomes very similar to a binary black hole signal, making it very difficult to see that there was even a neutron star in the system. That's one of the difficulty in determining whether a system is a black hole neutron star or a black hole system, is that when you get to a higher mass ratio system, there is basically no impact of the presence of a neutron star on the gravitational wave signal and no electromagnetic counterpart. The division between these two potential outcomes is shown on this plot here. You can see the spin of the black hole on the vertical axis, the size of the neutron star on the horizontal axis. This is all for a 1.35 solar mass neutron star. The different y curves show the different mass ratio, and if you go to the bottom left of this plot, you are not disrupting. If you go to the top right, you are disrupting. So an equal mass system is very easy to disrupt. Even a non-spinning black hole can disrupt an 11, 12 kilometer neutron star. But if you go to higher mass ratio, more typical to what we expect to observe, you need a significant positive spin on the black hole in order to disrupt the neutron star. And that is why, by the way, we do not expect the first two black hole neutron star system observed by LIGO and Virgo to have disrupted, is because they are at higher mass ratio, but with negative or near zero black hole spins. And so we would not expect disruption in that case. For neutron star systems, there are similar effects that can be used. The most useful probably is the fact that there's a threshold mass beyond which the system is going to rapidly collapse to a black hole. And at least for near equal mass system, if you get close to that threshold mass, all of the matter is going to fall into the black hole before forming an accretion disk. And so you're also going to prevent bright electromagnetic counterpart. This is shown on this plot here, where you see the disk mass as a function of the ratio of the total mass of the system to the threshold mass. And you can see that above about 95% of the threshold mass, you basically have no mass left in the disk. But this only really works for near equal mass system. As you get to higher mass ratio, it's probably not the case anymore. One of the neutron stars is going to form a tidal tail, and you can form an accretion disk from there. And exactly what happens when you get to higher mass ratio is more uncertain at this point. Typically, if you want to predict the amount of mass ejected during merger and the amount of mass remaining in the accretion disk after merger, at the moment we can do that for black hole neutron star system with accuracy of maybe 10 to 20%. But for neutron star merger, where the physics is more complicated, we only have accuracy of maybe 50% or so on the relative error for these quantities. So this means that our model for kilonovae for neutron star mergers are going to be more uncertain. I'm going to skip this. Say that the last part that we need to model for kilonovae is what happens to the accretion disk that remains after the merger. We have a black hole or neutron star surrounded by an accretion disk, which is maybe 10% of solar mass, 20% of solar mass. And at that point, there's a lot of complex physics that goes into the simulation. At this point, no numerical simulation is really capable of capturing all of the physics, magnetic field, neutrino transport, general relativity, that needs to be included over multiple seconds to follow the evolution of this accretion disk. So there's huge uncertainties in the amount of mass that is ejected in this post-merger remnant and what its properties are. Give you an idea of what we know. We do know that about 15 to 50% of the mass of the disk is eventually going to be unbound if you have a black hole plus this system. It could be even more if you have a neutron star plus this system. And the large uncertainty here is largely due to the large-scale structure of the magnetic field after merger. But unfortunately, current merger simulations cannot properly predict what that large-scale structure is. And so at this point, we are left with this being just an uncertainties in our kilonova models. The other important source of uncertainty is that the longer simulations that have been performed did not include advanced neutrino physics in the simulation. And so they cannot reliably predict the composition of the outflows. And so while we have a vague idea of the mass of the outflows, we don't know the composition very well. And it's very hard to then to predict what the outcome of nucleosynthesis is and what the properties of the kilonova are. So that's where we are right now. In this modeling of matter outflows, the in-spiral merger phase is qualitatively well understood. And then in the post-merger phase, we have an idea of how to evolve these systems, but the initial conditions in terms of the large-scale magnetic fields remain an important problem that is going to impact our predictions for the matter outflows. And we still need simulations with better neutrino physics to properly model the composition of the outflows after merger and thus the outcome of nucleosynthesis. That is still limiting our ability to actually use kilonovae to extract information about the properties of the merging object at this point. Thank you.
Thank you. Thank you for the nice and a nice talk full of lots of details. Are there any questions? Please raise your hand with them. You can find your hand in the reactions menu. Sorry about that. KG, please go ahead.
Yeah, hi. It's a nice talk. Thanks for the detailed update. I was wondering whether at this stage of the accuracy, do you also track the recoil, gravitational recoil, and is it accurate? Accuracy is good enough to come up with some kind of fitting formula like we have for binary black holes?
So we can measure the recoil. It has been done in a few simulations for black hole neutron star merger. I'm certain we've done it a few times. I don't know if we have enough data to really do fitting formula yet. One complication compared to binary black hole is that part of the recoil is due to the matter ejection and not just the gravitational waves. And so once you get significant disruption of the neutron star or significant matter ejection in neutron star merger, just looking at the momentum carried by the gravitational wave is no longer sufficient to model the recoil. But yeah, we do have a few simulations of higher mass ratio, high spin black hole neutron star that allows us to look at how that impacts the recoil, which then in the order of a few hundred kilometers per second, I think, for these disrupting systems. I'm not aware off the top of my head of a fitting formula existing for the recoil for these systems yet, but yeah, I don't think that there has been enough simulations with the reported recoil velocities for that to exist at this point, as far as I know.
Yeah, thanks a lot. Yeah, no, thanks a lot.
Thank you. There's a question in the chat from Divjot Singh. How long do these simulations take and how computationally expensive are they?
Depends a fair amount on the accuracy you want and the amount of physics, but order of magnitude, it can take from a few weeks to a few months to run them. And from, let's say, 100,000 CPU hours for the cheapest, less physics intensive simulations to, I think there have been simulations that have gotten close to 100 million CPU hours for the highest resolution simulation with magnetic fields that have been performed, but more typically in the order of 500,000 to 1 million CPU hours for most simulations run today, I think.
Thank you. Well, I wanted to ask a very brief question. For 1908-14, as you probably know, that was one of the objects was a 2.6 solar mass object, and we couldn't tell whether it was a neutron star or a black hole. How much larger should the signal have been to be able to distinguish a neutron star from a black hole in the merger?
At this point, for a system like that, numerical simulations are not capable of capturing the presence of a neutron star. So I can't even give you an answer. It's such a small effect, the presence of a neutron star, that I can't even give you an answer. But it's going to be large, very large.
Okay.
We did a simulation at some point of a mass ratio 6 system, which is better than what 1908-14 is, non-spinning, and we couldn't even measure the finite size effects in the neutron star. This one is it's nearly a mass ratio 10, right?
Right.
So it's going, and it's a very massive neutron star. If it is a neutron star, and very massive neutron star have even lower tidal effects. They're very compact, right? So I mean, yeah, I don't have an idea, but it's going to be a ridiculously large number.
Okay.
We really need a lower mass neutron star to be able to do something, and ideally lower mass black hole as well. Okay.
And Sal was asking probably the last question we can take. How do we get the next generation of neutron star black hole or binary neutron star simulations and get waveforms that we can trust at SNRs of 1,000 or thousands?
Yeah. So I mean, there's definitely work currently being done on getting simulations that can take advantage of exascale facilities. I know quite a few groups have different ideas for that. I'm aware of code using wavelet methods, of code using discontinuous Galerkin method, and so on. So these codes should be able to run to much higher accuracy, but I don't know if it gets to SNR of 1,000 with current computing facilities. At least that seems a huge jump compared to what we currently can, which is more, I think, a scenario of 30 to 50, something like that, if I remember. So getting to 1,000 is going to require more than just the new code we are currently looking at. I think we won't get a jumper factor of 100 in one go. But we're definitely working to at least get to orders of magnitude improvement in the computational resource that we can use, which with code that scales currently at third order, and hopefully in the future better than that with the new methods, can actually significantly improve our accuracy.
Thank you. And Salvo says, and I agree, that to be fair, we have many years, about 15 years to figure this out.
15 years is not such a...
Doesn't mean we shouldn't be doing it.
15 years, we need to work
okay.
on it. We need to work on it already.
Yeah. Well, thank you again. Thank you for a nice talk. And we'll hear next from Chiara Mingarelli. She's an assistant professor at the University of Connecticut and also a scientist at the Flatiron Institute. And she will tell us about another frequency, gravitational waves of yet different frequencies using pulsar timing arrays, the next window to open the gravitational wave universe. Go ahead, Chiara.
Wonderful. Thank you so much. I'm delighted to be here to talk to you all today about nanograv and the latest results to come out of our collaboration. So before we get started, I just wanted to acknowledge our many observatories and collaborators all over the world who have come together to make this kind of science possible. And I also want to acknowledge OSGRAV for doing such a great job for organizing this meeting. And also thank you to Gabby for chairing this session. So the outline is as follows. I'm going to situate us in the low frequency gravitational wave spectrum where pulsar timing arrays operate. And then I'm going to walk you through the nanograv 12.5-year results. Then I'm going to focus a lot on the future. And if you have some ideas about what you would like to see us do with the nanograv data, please don't hesitate to send me an email. I have my email address here, and then I've also included it on the last slide in case you get an idea during my talk, fingers crossed, and you would like to share that with us or potentially collaborate with us. I feel like I should also warn you that a thunder and lightning storm has just started. So hopefully my power doesn't go out and everything will be fine. I should also warn you that I have a small French bulldog that snores and farts. So any kind of snoring I will take to come from her and not from the audience. And any kind of flatulence will also be attributed to Coco. So for those of you who are experts who want a sneak peek on what the punchline is, I'll let you know right away, and then that'll also maybe motivate you to follow the different points, is that we expect to detect the gravitational waves background very soon. We have not detected it yet. We have not claimed to have detected it yet. We expect the first detection of continuous gravitational waves from individual supermassive black hole binary systems to follow 5 years. After the detection of the background, and at least by the end of the decade. And after we can subtract the gravitational wave background, which is in fact a foreground, we just call it a background for historical reasons, but this is the signal we're looking for. But once it is the background, we can subtract it and the continuous waves, and we should be able to see the underlying anisotropy in the background. And then we will happily be in the LISA era. So Sarah and Francois both gave us some really great talks about higher frequency gravitational waves. So Francois's talk was, really focused on the LIGO band, which is sensitive to black hole neutron star mergers, binary black hole mergers, binary neutron star mergers, but really focuses at these high frequencies at hundreds of hertz to a kilohertz. Sarah walked us through the LISA experiment, and here we expect to be able to detect extreme mass ratio in spirals and massive black hole binary systems. Now here, when I say massive, I mean about 10 to the 5 to 10 to the 6 solar mass black hole mergers. And this happens in the millihertz regime. With pulsar timing arrays, where I'm going to be focusing this talk, we are sensitive to the most massive black holes, and these are anywhere between 10 to the 8, 10 to the 9, and in some rare cases, 10 to the 10 solar masses. And these live in the centers of galaxies. And when galaxies merge, the supermassive black hole should merge. So today I'll be focusing on the nanohertz gravitational wave band. So I want to really emphasize that these 3 gravitational wave detectors are complementary. And for the experts on the call, the ISCO frequency of our supermassive black holes is at around 10 to the minus 6 hertz, which means that they merge before they enter the LISA band. So PTAs and LISA really are sensitive to different sources. Another thing that might boggle your mind is that, whereas right now we're used to seeing these waveforms and beautiful signals that last a fraction of a second, pulsar timing array sources are in band for about 25 million years. So we are in the slow in spiral phase of supermassive black hole mergers. So we're not seeing the final chirp like LISA and LIGO will. We are seeing this slow in spiral. And another thing that might be useful to kind of, for your mental mind maps going between LIGO and LISA to pulsar timing, is that it's more intuitive to think about the strain as a change in time over time for pulsar timing, rather than a change in distance over distance. So for example, we know that the signals that we're looking for from our models have a strain of about 10 to the minus 15. And say that your data set has about 10 years of data, and you can convert this into seconds by having, pi times 10 to the 7 seconds per year. This gives you a residual or a timing precision that you need to detect these signals of about 300 nanoseconds. So 300 nanoseconds is pretty small, but is very achievable for millisecond pulsars. So that's 300 nanoseconds over about a decade. And if you want to go back into change in distance over distance, that's about a few meters per light year. And so while that seems kind of infinitely small, these signals are the strongest sources of gravitational waves in the universe. So we come in at a whopping, 10 to the minus 15 to 10 to the minus 16, whereas the other experiments have exquisite higher frequency and lower strain precision. So let's get us started with a little animation of how supermassive black hole binaries form. So galaxies have massive, supermassive black holes at their centers. And when these galaxies merge, their supermassive black hole should merge. Now the merger starts at about a milliparsec. And these supermassive black holes are, again, the most massive ones. So here you can see this kind of 80s space-time fabric coming out of the screen, coming right at us. And this is an animation of the gravitational wave signal. So the gravitational waves are emitted in all directions from these supermassive black hole binary mergers. And some of them make their way towards our galaxy. Now in our galaxy, we're timing these millisecond pulsars, and they have these ultra stable arrival times. And so as the gravitational wave transits in our galaxy, you can potentially see the pulsar signal arrive a little bit early or a little bit late, since the gravitational wave signal changes the proper distance between the Earth and the pulsar. Now, if you were to see this signal in just one pulsar, that could be anything, right? Between the Earth and pulsars, which are typically at a kiloparsec or around 3,000 light years away, you have gas, you have dust, there's this interstellar medium. There's so many things that could be causing a fake signal or a fake kind of blip. And so we look for the signal not just in one pulsar, but in an entire array of pulsars. So in the NanoGrav 12.5-year data set, which I'll be talking to you about today, there are 45 such millisecond pulsars. And with our international colleagues in the IPTA, there are about 60 of these. So the International Pulsar Timing Array, and in fact, pulsar timing arrays in general, are a key project in radio astronomy. Not only do we have, in North America, we have, or had, I'll talk about that at the end, Arecibo, the VLA, GBT, and CHIME, which is a relatively new radio telescope in Canada. But in Europe, we have Nancy, Westerbork, we have the Jodrell Bank telescope, and we also have the Sardinia radio telescope. In South Africa, Meerkat is causing quite the commotion. It's a square kilometer array pathfinder that's done some rather exquisite pulsar timing. So believe in an email from Matthew Bales, this was down to around 10 nanoseconds for one of the best pulsars. So really impressive stuff happening in South Africa. GMRT is in India, and they're our newest full partners in the International Pulsar Timing Array. And in China, we have FAST, which is this 500-meter diameter telescope. It's absolutely enormous, and it has fully deformable mirrors, which is very cool. In Australia, we have the Parkes Pulsar Timing Array, and they use the Parkes Radio Telescope. So how do pulsar timing arrays actually use pulsar data to find gravitational waves? So right now, I'm going to focus on the gravitational wave background. And so what you have here in this first image at the very top are the residuals from a pulsar called J1713 plus 0747. And so for those of you who aren't familiar with pulsars, this is of course a gravitational wave meeting. The first few digits are the right ascension, and then the last ones are the declination of the pulsar. So if you have the pulsar name, you know where to find it on the sky. So we've been timing this pulsar for, as of now, about 15 years. The data shown here are from 12.5 years. And this was recently published. The corresponding author is Megan DeCesar, who shared this image with me. So these are the residuals of this pulsar. And the residual is the expected minus the actual time of arrival from the pulsar. So a gravitational wave signal would introduce a kind of red noise. This is a noise that establishes itself over long time periods and grows as a function of time. So we call this red noise. Now in 2012, there was a back-end upgrade, and you can see that the residuals got much, much better afterwards. So the different colors correspond to different telescopes that are observing this pulsar at different frequencies. So this is one of our best pulsars. This, as you can see, is a pretty spectacular pulsar. There's no intrinsic red noise in this pulsar that we can see right now in this data set. And that's important because the gravitational wave background signal itself is a red noise process, which means that if a pulsar is plagued with its own red noise, a kind of unmodeled noise that establishes itself over long periods of time, it's really difficult to disentangle that from a gravitational wave background signal. And therefore, it's not so useful for gravitational wave searches. Now, there's currently about 2,300 known pulsars, and about 10% of them are millisecond pulsars. But there's not going to be a shortage of millisecond pulsars at any time in the future. According to most models, there could be up to 30,000 more detectable pulsars just in our own galaxy. So this is a galaxy scale gravitational wave detector. Now, the way that we look for the gravitational wave background signal is that we cross-correlate these residuals. So SAB, this is from these subscripts are pulsar A and pulsar B. This is the cross-power spectral density between two pulsars. Now, when you cross-correlate the pulsars, two things should pop out. One is this gamma AB function, and this is an angular correlation function. So the gravitational wave background introduces a common correlation between pulsars, which otherwise should have no correlations between each other, right? Each pulsar should have an independent noise realization, and a gravitational wave background signal would be present in all of these pulsars. So this angular correlation function is predicted by general relativity and was first written down by Hellings and Downs in 1983. And I'll show you this in a minute. The second part is basically a kind of amplitude term. And this is the characteristic strain. And that's the sum of the strain that's emitted by supermassive black hole binaries over their cosmic merger history. And so the characteristic strain can tell you about how supermassive black holes merge, if their orbits are circular. This is really an astrophysics term. And this correlation function is a GR term. This is more of a fundamental physics term and tells you what the expected correlation is between two pulsars. It's also a geometric term. So while we're used to seeing these beautiful LIGO images of the final chirp from stellar mass black holes, I want you to imagine now the galaxy and in fact our entire universe full of supermassive black hole mergers. Each one of these supermassive black holes taking about 25 million years to merge, meaning that you get a huge buildup of sources at low frequencies, right? Gravitational wave frequency evolution is very, very slow. And so you get a huge pileup of these sources at low frequencies, generating a stochastic or random gravitational wave background. Well, that's really good news for us, because when we try to go ahead and measure and model the characteristic strain, it's a function of the supermassive black hole binary population. So here, you can model the characteristic strain as the sum of the gravitational wave energy per logarithmic frequency interval with a cosmology term, your model of the supermassive black hole binary population, which itself depends on the number density of sources, and your black hole masses, the redshift evolution, and Q is your mass ratio. So when you integrate all of these terms, you get the characteristic strain. But you can in fact simplify this. So this dE by d log f term gives you a frequency dependence to the 2/3, and now you have a chirp mass term to the 5/3. And this function, this equation will really collapse into something that's much more palatable. So the two main features of the characteristic strain, in my opinion, is number one, if your binary orbits are circular, your frequency decouples from this dependence. And you have a frequency to the -4/3, which comes out. Now you still have this double integral, which depends on your supermassive black hole binary population. But what's interesting is that this characteristic strain depends strongly on black hole masses. So the strain squared depends on the supermassive black hole chirp masses to the 5/3, making pulsar timing arrays and the signals that we can detect extremely sensitive to supermassive black hole masses. And this is a nice key jumping point or jumping off point between optical astronomy and gravitational wave astronomy. So when we go and try to measure the characteristic strain, what we're measuring is this amplitude of the gravitational wave background, which is in turn just this double integral, or the square root of all of these terms. So hopefully when we measure this amplitude of the background, we can in turn start to understand the underlying supermassive black hole binary population and its masses and how this evolves as a function of redshift. The frequency to the -2/3 just comes down from here. And this part here in parentheses means that we have this power law behavior, f to the -2/3, that we reference at a reference frequency of 1/1. So because this is a power law, when we publish our papers, we all have to agree on a specific frequency that we report the amplitude of the gravitational wave background at, or else you could report it really at any frequency. So to make easier comparisons, we all agree that we report the characteristic strain's amplitude at a reference frequency of 1/1. Now, for those of you who are interested in cosmology, and you may also be going to Chiara Caprini's talk later on, you can also write down the characteristic strain as omega GW. So the next thing that we're going to look at, now that we are all masters of the characteristic strain of the gravitational wave background, is this correlation function here, gamma AB. So before we do that, the last thing I want to just highlight is that this characteristic strain really depends on the astrophysics of supermassive black hole mergers. And in a few slides, I'll show you exactly how we can decompose the characteristic strain into all of these different components. But now we have to talk about this correlation function. So when you have a pulsar pair, for example, that's separated by 20 degrees on the sky, the correlation between these two pulsars, this correlation function predicts that you should have a value of 0.3 and that this is positive. When you have your pulsar separated by almost 180 degrees on the sky, you get a correlation value of just above 0.2. If your pulsars are separated by 40 degrees on the sky, very little correlation is introduced by the gravitational wave background. and so on and so forth. So this is really a point-by-point function. If your pulsars are separated by X degrees on the sky, this is the expected correlation value. Now, in the limit of having an infinite number of pulsar pairs, you can fill out the Hellings and Downs curve. That's this blue line. And so it looks here like it's a continuous function. And of course, we can model it as such, but it's really a pulsar pair by a pulsar pair function. It gives you this nice blue line. So when we detect the gravitational wave background, what we have to do, first of all, is to see if our own measured pulsar pairs follow this kind of shape. And then the amplitude of the gravitational wave background is going to be set strongly by this characteristic strain term. So the amplitude of the background will tell us, where this exists and can move things up and down. And the correlation function will give us the shape of how those residuals are distributed here. So for the Hellings and Downs curve, we intrinsically assume that the gravitational wave background is isotropic, but that may or may not be true. In this talk, I'm really going to focus on supermassive black hole binaries as the source of this gravitational wave background. But people have been having a lot of fun recently modeling it in terms of cosmic strings and primordial black holes and lots of really exotic fun stuff. And I'll talk a little bit about that too. So these pulsar correlations can create this curve, and this curve can of course change if we have alternative theories of gravity or if there are departures from isotropy in terms of our gravitational wave background. So let's get down to the core of the talk. What do the NanoGrav 12.5-year data show? Well, first, I'm going to walk you through what are on the X and Y axes. So here on the X-axis, we have the amplitude spectral density of this SAB function. Now you'll remember there were two components that went into it, right? There's your Hellings and Downs curve, or your modulation of the residuals, and then there's the characteristic strain squared. And then that gives you a kind of amplitude of the background. So here we're not including the cross correlation, so there's no gamma term. And what we've plotted is the square root of this SAB function divided by t, which is the total time span, or 12.5 years. Now, this dashed line is 1 over a year. And because we transform all of the pulsar arrival times to the solar system barycenter, anything that has a period of exactly 1 year is probably the Earth. And so we just say that we don't have any sensitivity at that frequency. Now you can see at high frequencies, things look really noisy. And that can be for multiple reasons, but mostly because our bucket sensitivity is at 1 over our total observation time. And so in this case, our bucket sensitivity would be at 1 over 12.5 years. So up here, also at high frequencies, the stochasticity of the gravitational wave background, or the number of sources that are there, is also decreased, because now your black holes start taking off and merging at those higher frequencies. So there's two reasons why there could be more noise at these higher frequencies. Now, what's going on at these lower frequencies? That really is the question. So if we model what's going on up here as a power law and just look at the last 5 frequencies, we get something that looks a lot like what we expect for the gravitational wave background with these 5 lowest frequencies. If we allow the spectrum to turn over and have a broken power law, then it prefers to turn over here between these 2 frequency bins, between the 5th and the 6th bin, and then it becomes flat up here. So it can, it's just noise at higher frequencies, and at lower frequencies, there's definitely something in the data. Now, when we do the gravitational wave background analysis, we assume that there are 30 frequencies. And so if we require the power law to go through all 30 frequencies, regardless of what we know about astrophysics and our detector, then you get this green line. And so what about the spectral index? Can we simultaneously model the amplitude of this signal, and we'll call this a common process because this is found in the 45 millisecond pulsars in the nanograv 12.5-year data. We're not really sure what it is yet, but if we assume that it has some amplitude and spectral index, then we get these different contours for these different models. So if we, impose this green dash dot line model, this power law, then you get this green contour here with 1 sigma, 2 sigma contours. And if you allow instead your model to break, going from low frequencies to high frequencies, you get these 2 lines here. Now, just to remind you, when we're working with gamma, these gravitational wave background from supermassive black hole binaries has a value of gamma is 4.3333, and that would be right around here. So this is looking pretty interesting. Now you're probably wondering, well, if it's not gravitational waves, then what is it? Well, maybe it's something that we haven't thought of. In the nanograv 11-year data, we found Jupiter. And so what happened here was that there was this peak in the amplitude PDF. So here we have a log of the gravitational wave amplitude and the PDF. And as we change the different solar system ephemeris models, and for people who haven't heard about the solar system ephemeris, this is where the planets are in their orbits and their masses. And this is important for computing the solar system barycenter, or the point where you can balance the solar system on the tip of your finger, so that when you transform all of your time of arrivals to the solar system barycenter, you're transforming them to the correct spot. So yeah, we found that
there are 5 minutes left.
Yep.
5 minutes left.
Okay, great. So we found that when we changed the solar system barycenter model, that this peak started disappearing. And so Michele Vallisneri led a team that created Bayes FM, which got rid of this fake model that was likely due to inaccuracies in the orbit of Jupiter. So with the nanograv 12.5-year data, when we assumed a fixed solar system barycenter, we find that there is a signal with an amplitude of 1.9 times 10 to the minus 15. And what about the Hellings and Downs curve? Do we see the Hellings and Downs curve? Because you remember, you need to have these 2 things. So pick a point and try to focus on it and see what you believe. This is the nanograv 11-year data. And now we move to the 12.5-year data. 11 years, 12.5 years. So now that you've chosen what you will believe, you might want to know something a little bit more evidence-based. So what is the evidence for the Hellings and Downs curve? Well, right now we have strong evidence for there being a common amplitude process. We know that there is something common in these 45 millisecond pulsars. And in fact, there's a Bayes factor of 10 to the 4.5 to 1 for that being a common amplitude process rather than just intrinsic pulsar noise. So there's something there. But what is it? We don't find strong evidence for Hellings and Downs correlations at all. So it's something interesting, but we need more data to figure out what it is. And so what's next? Well, the nanograv 15-year data set is next. And here we have all of the data releases from nanograv from 5 years all the way up to 15 years. And Joe Sugim is taking the lead on this. The 15-year data set is very interesting. It has 68 millisecond pulsars with timing baselines up to 15 years. And with this data set, we're going to try to see if the signal to noise ratio of the common process is increasing. Is the significance of the Hellings and Downs curve increasing? And this timing analysis is in progress right now. And we are not sharing any results right now. We are doing a very, very careful analysis. And so what else is next? What could we do? Well, right now, in terms of the landscape of different gravitational wave background models, there only seems to be one winner, and that is this model that Alberto Cesana came up with in 2013, which is really a Monte Carlo of many, many models for the gravitational wave background. Because we hadn't been detecting a signal for so long, people really started sweating and coming up with really interesting astrophysics to explain why we weren't detecting a signal. But in fact, perhaps all of that was unnecessary. Another thing that we can do that I promised to come back to, and I'll do that here, is decomposing the characteristic strain in terms of the supermassive black hole binary mass, number density of sources, and the minimum black hole mass that's contributing to the background. So if the nanograv signal really is from supermassive black holes, we can tell that the number density of sources is something like 7 × 10⁶ binaries per megaparsec cubed, that the minimum mass that's contributing to the background is about 10⁸ solar masses, and that the mass ratio of the sources is probably greater than 0.25. We can also try to understand when we're going to detect the individual supermassive black hole binary systems. So some simulations show that those supermassive black hole binaries, the individual ones, could be traced by periodic light curves. And right now there's a huge multi-messenger effort to identify the host galaxies of these supermassive black holes. So some of the most interesting host galaxies have been identified in the CRTS catalog. The most promising one right now looks like it's HS 1630 plus 2355, which is serendipitously aligned with one of the nanograv millisecond pulsars, giving it a stronger signal than it would normally have. And that's a new result from the Shin et al. Paper. Knowing the sky location is really important. If you know the sky location of one of these host galaxies, you improve your strain by a factor of 2. Even better, if you have information on the frequency, you can improve your strain by an order of magnitude. But that's not all. You can also modify your correlation function. So I was very explicit that the Hellings and Downs curve is for an isotropic and Einsteinian gravitational wave background. But if it's anisotropic, here I have the correlation functions for a dipole, everything changes. Here you have a quadrupole, and so on and so forth. And then you can have departures of GR. Here in Wenzer et al., you can see a breathing mode, for example. If you have this additional polarization, you have something that looks completely different from the Hellings and Downs curve. And so searching for anisotropy is something that's going to be really interesting to do after we detect the gravitational wave background. And next, of course, are our new telescopes. So tragically, Arecibo collapsed on December 1st, 2020. And I think a lot of us still get emotional thinking about the webcam, or it was a drone view of the collapse. As Nanograv, we've restructured the observing program to move some of the pulsars that were being timed by Arecibo to the Green Bank telescope. And then the low frequencies that we were timing at GBT have been in turn offloaded to CHIME. And we've also got time on VLA on the Very Large Array to make timing observations at higher frequencies. The Green Bank telescope's ultra wideband receiver is going to be a game changer. With this ultra wideband receiver, you just do one pointing and then you can time all of these different frequencies, meaning that you don't have to do a high frequency observation and a low frequency observation. You can do everything at once. And of course, there's new facilities that we're all very excited about, like NGVLA, DSA 2000, and possibly a future Arecibo facility. And of course, I would be remiss if I didn't mention Meerkat and the SKA, which are going to be fantastic new facilities. So I'd like to remind you that there were a lot of talks on day 2 and 3 related to pulsar timing and with posters, and that later on today, there's tons more of pulsar timing array science that's going to be discussed here at Amaldi. So in summary, I want to remind you that PTAs are really an interdisciplinary and multi-messenger science experiment. We have global radio campaigns. I didn't get to mention Gaia today, but please ask me about that later if you're interested. We can do tests of fundamental physics, galaxy evolution, and there's something in the 12.5-year data. It has a common amplitude and spectral index in all 45 millisecond pulsars, but what is that? If it is a gravitational wave background, then with 2 to 3 more years of data, we should be able to make a detection. We also should be able to detect at least 10 local sources or AGNs that may be hosting binaries by the end of the decade, with a characterization of the background through measuring its anisotropy to follow, and then Lisa. So what's next? Everything is next. This isn't even the beginning. This is the prologue of a beautiful story for pulsar timing arrays. So thank you for your attention.
Thank you, Chiara. That was great. It's amazing how interesting, how exciting gravitational wave astronomy has become in the last few years.
Thank you. I certainly think so.
So we have some questions in the chat. Aditya Tamar asks, does NanoGrav expect collaborating with future iterations of the Event Horizon Telescope to observe pulsar signatures from Sagittarius A and study complementary science goals like GR test, black hole mass and spins, etc.?
So let's see. So right now, the EHT isn't really imaging horizons that are likely to be binaries. But what's really interesting, in my opinion, are the mass measurements of the black holes, because when we try to compute the amplitude of the gravitational wave background, we make a scaling relation between the black hole mass and the host galaxy's mass. This is an empirically derived formula where you can switch from one to the other. Now, when EHT measured the mass of M87, it found that the stars were a better tracer of the mass rather than, the gas estimate. And that was really unexpected because the gas is much closer. People thought the gas measurement would be better. And so now this could be a new and interesting data point in constraining this relationship between black holes and their host galaxies, which in turn will feed into our gravitational wave background models. Now, detecting things like spin will require a few more years of work for the individual sources. Because our sources evolve so slowly as a function of time, there's not a lot of frequency evolution happening in a 10-year pulsar timing array observation, no matter how fast your black holes are spinning. However, if we can measure the gravitational wave perturbations at the pulsars, it might be possible to coherently concatenate all of these pulsar observations and recreate a waveform that spans from the Earth to the pulsar. And there you have 3,000 years of a waveform. And that is, in fact, sensitive to spins. In fact, up to 2 PN post-Newtonian terms can be measured in that way. So that's something that we hope to do maybe in the next 10 years. But it's definitely something that we're very excited about.
Thank you. Ricardo Busquiccio asks, he first says, thanks, Chiara, for the great talk. Are all the Arecibo millisecond pulsars observed somewhere else now? And how long would we need to wait to have a lower frequency beam measurement?
When we fold in all of our international partners, yes, those pulsars are all being covered. And that's one great thing about pulsar timing arrays, is that there's no single point of failure. In the IPTA, we have 9 radio telescopes now. And while Arecibo will be greatly missed, there were problems with Arecibo before. So we were already thinking of contingency plans in case it was defunded or decommissioned. And so FAST can see all of the pulsars that Arecibo can. And in fact, if I go back here, NGVLA and DSA 2000 would be even more sensitive than Arecibo. And in fact, these smaller arrays would also give you more declination coverage, because now you don't have to worry about your telescope falling over if it points down too far. So this new way of arranging radio telescopes and having these larger arrays of smaller telescopes is probably the way forward.
Thank you. Alan Weinstein also says, wonderful talk. You said that the red signal is in all the 45 millisecond pulsars. Is that really so? Or is it only after averaging all 45 that you see the red signal?
So let me go back to the slide here. So this is one amplitude spectral density that all of the 45 millisecond pulsars share in our Bayesian model. And so the signal can be stronger in some pulsars than in other pulsars. But this ASD is shared by the 45 pulsars.
Thank you.
And thank you. Thank you everyone for your very nice words. I have said many words too. So sorry for going a bit over.
This is probably the last question. Joris van Heesmingen asks, you mentioned you gain if you know the source location. If you don't know the location, can you extract them from the angular cross correlation? And if so, is pile up from background the problem?
Oh, what a very perceptive question. So we do in fact do all sky searches, and all sky searches take a lot of computational effort because you're computing if there's a detection at each pixel on the sky, and then you're going over your entire frequency space. And so this is a huge computational feat. So all sky searches are done, but are a bit of a pain and are not as sensitive as doing targeted searches. So I focused on targeted searches here because in my opinion, this is the answer to that problem. You gain better sensitivity if you follow up some AGN that are looking kind of interesting, according to our, multi-frequency, multi-wavelength electromagnetic colleagues. And it could potentially be more efficient than just doing all sky blind surveys. Now, your question about the pileup from the background is great, because if we don't subtract the gravitational wave, let's call it a foreground signal now and be very optimistic, then you have an additional red noise term in your pulsars that's not modeled, and therefore they're not as good for detecting any signal. And so this could push our detection capabilities back by maybe about 5 years. So I looked at this in a 2017 paper, and I found that, by the end of the decade, we could detect about maybe confidently 2 nearby supermassive black hole binaries in the 2 mass volume, which is 225 megaparsecs. And if we didn't model the red noise, like if we couldn't manage to subtract that gravitational wave background signal, that it would be hard to detect even one. So it's going to be really important to model and then take care of the gravitational wave foreground signal. But this is, of course, a wonderful problem to have. So I hope that we have this problem very soon.
Great. Yes, it's all subjective of what somebody calls signal and somebody calls noise.
Exactly. Okay,
well, thank you again, Chiara, and thank you to all the speakers today. I want to remind you all that there are related topics, parallel sessions later in day 4, and day 5 has a keynote diversity and inclusion talk and another plenary and parallel sessions. So I hope to see you all there. Bye now, and thank you all.
timing array session. Bye, everyone.
Bye.